All right, good morning, everybody. Today we have started the month of November, and today is November 4th, Monday, and we are discussing ES 1060, and the subject matter we're going to talk about today is statistics. We're going to have a fairly short lecture today, but I want to refer you to something on our Moodle page. If you go through our page, assuming I can scroll down, there's a lecture here that says Chapter 6 Statistics Lecture on November 13th. That was recorded last year, but it's still, nothing has changed in the world of statistics. So if you watch that lecture, you're going to pick up on a whole lot of information. But what I'm going to talk about today is statistics is a body of math that I'd like to mention two things about. One is the purpose of statistics is to describe data. And I'll talk about some examples of this, not only in this, but also on the November 13th lecture from last year. And the point of the lecture today is calculating statistics is boring and error prone. And using Excel is the best. Using Excel will make your life better because Excel will do all of the drudgery for you, and it will also eliminate any mistakes except for the possibility that you choose the wrong formula or input the data incorrectly, each of which is quite easy to correct. So I really love to use Excel when I'm analyzing statistics. Even to the point when I was finishing my PhD, I have a minor in quantitative research methods, which means analyzing statistics. And there's a huge, very standard industry program called SPSS, which has been around since probably before I was born, and definitely before you guys were born. And it's big and cumbersome and does all kinds of stuff, but it makes your data a little bit inaccessible. But I used this program to do my final analysis, but I started everything in Excel. And Excel will do everything that SPSS will do for smaller data sets. So unless you have 80,000 points of data, Excel really will do almost everything for you. So what I said, the purpose of statistics is to describe data. What do I mean by that? Well, what does that mean? Well, what it means is, let's talk about something like, if somebody asks you a question and they say, what is the average price of a home in Cowley, Wyoming? Okay. And let's just say that there are 5 homes available and 4 of them are $100,000. I know this is greatly oversimplified. And then somebody came in and built a beautiful home on the hill for $2.5 million. Okay. Now, if somebody asks you for the average, the real way to do an average is to add all of these up, to take all of those data points and divide it by the number of data points in the set. Okay. Do you think this is going to give you an accurate reflection of the price of a home in Cowley, Wyoming? It's not, is it? Because what they're really getting at, I mean, most of the time when people ask you this, what they're asking is, if I were to move to Cowley, Wyoming, how much money would I have to spend to buy a typical home? And this obviously is an atypical home. Okay. Another thing that I like to do, so this is, in other words, so while the average is mathematically correct, it does not describe the data set. It does not describe the price of a Cowley home. So what does that mean? We just use the average because mathematically that's okay. Well, from an engineering point of view, that is repugnant. That does not make any sense whatsoever. The next data set that I'll give you, and I use this with permission, I will not use any names, but in the STEM division, we have about 16 people. And I tabulate the number of kids we have. So basically, I'll just put down numbers for each of these people. This would be the faculty member. And then the number of children that they have. And we have somebody who has 3 children, 0 children, 1 children, 0 children, 0 children, 11 children, 0 children, 2 children, 2 children. 3 children, 2 children, 2 children, and 1 child. So there are 13 people in this data set. I included some people who aren't really there. Okay, so once again, if we ask what's the average number? Well, if we add all those up, what's this 11 going to do to the data set? Yep, it's going to pull it up. So this is really an outlier, isn't it? Okay, so what that means is, once again, if an average doesn't describe a data set, how else can you describe it? Well, you can describe it using what's called a median or what's called a mode. And what a median is if you lined up these numbers in order from the smallest, 0, 0, 0, 0. So there's 4 zeros, a couple of ones, 1, 2, 3, 4 twos, and a 3, and a 3. And you found the data point in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I missed somebody, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have a 3 and a 3. Oh, I have another. No, I got a 3 and a 3. Got you. And I have 0, 1, 2, 3, 4. I have 5 zeros. All right, there we go. So there's 13 data points. The median is the point right in the middle. So if there's 13, it would be point number 7. So the median is 1. Okay. And then what is the mode? The mode is the number that occurs the most often. So we have 5 zeros, 2 ones, some 2s, and some 3s. 5 zeros is the most. So the mode of the data set is 0. The median is 1. And we could find the average really quickly on Excel. I could do it in my head, but I just as soon do it on Excel because that's our class, right? So we have 5 zeros. And then we have 2 ones. We have 4 twos. And we have a couple of 3s. All right, so how do I find an average? Well, one way is to add them all up using the sum feature and then divide by the number of data points. The other way to do it is we can, let's do this. Look up a function and it will tell you there's my average, and the average is 1.23. I missed the 11. I was going to say I missed number 11. Oh yeah, he's way down here. So let's scoot this. And let's put 11 right here. All right, so that brings the average up to almost 2, doesn't it? So the average is about 2. Anyway, but you can see that 2 doesn't really describe the data set very well. 1 doesn't really describe the data set really well. What happens is we just have an outlier. We have everybody clustered, and this is the kind of data that tends to cluster toward a particular number because most people don't have 57 children. So there's sort of an upper limit on how many children most people have. Now, that's not entirely true, but in the scheme of normal things. Other data that sort of clusters, let's come over here, around numbers is like height or weight, okay? But if we look at height, for example, there are differences between men and women. Men tend to be taller than women. That doesn't mean that there are many tall women and many shorter men. But in general, the average height of a man is about 5'9". The average height of a woman is about 5'4" or 5'5". Let's just say 5'5". All right. Now there are outliers where you see NBA basketball players who approach 8 feet tall, and you see people with congenital conditions that they might approach 3 or 3.5 feet tall. But in general, everybody clusters around this number. So that's where this idea of a bell curve, which is really called a normal distribution, occurs. And all naturally occurring data, if you gather enough of it and you gather it properly, will follow a natural bell curve, which means that the average, the mean, and the median will be the same, and then it will drop off in a particular numeric fraction equally on both sides until you come out with these little tails. So this number is called X bar, which is the average. And if you go out a certain amount, you can capture about 2/3 of the data. And that is called a standard deviation. Or if you want to be fancy, that's one standard deviation below the mean and one standard deviation above the mean. Okay. And if you go out that same amount, say this is, I don't know, 5 inches, I'm making this up. If you go out another 5 inches, that would be 2 standard deviations. And if you go out into the 3rd standard deviation, that would be another 5 inches. And what you get then are these little residuals on the end. And almost that becomes rare. Okay. So anything that happens out here happens, but it doesn't happen very much. And there's some really strange things with this. Like, for example, in American baseball, they have followed baseball so closely. And I don't know, baseball people are just a breed apart. And we actually have a very well-known baseball writer here on campus. I will not reveal their identity, but they are statistics fiends, and they know exactly what every game is going to look like. So when you get somebody like a really amazing baseball player like Shohei Ohtani, who just injured his shoulder, by the way, so we don't know what's going to happen with him. But when he starts doing things that are out of the norm, he's really acting up here in the 3rd standard deviation, and it's really unusual. So they get really excited about that to try to see what's going to happen with those things. There's another one, and then it's the last thing I'm going to talk about today, except to say, don't try to do this at home. Use Excel, and then when you take your statistics course at ISU, you're going to be really happy because you're going to say, I don't have to do all that stuff. So, and you will be happy. There's a measure of intelligence, which is called intelligence quotient, or IQ. And this is also something that has been studied for years and years and years. I mean, for decades. And the idea of IQ is how much natural intelligence do you have in different fields, like problem solving, spatial reasoning, mathematics, verbal, all of these other things. And so IQ correlates with a lot of different things, but also want to be clear, it doesn't correlate with everything. So there are very many successful people who are not in the toppest of top IQ brackets. And there's actually some things that start to go along with people in very, very high IQ brackets that are kind of different. But the normal IQ distribution is standardized at an average, an X bar of 100, which means that the average person will have an IQ of 100. Okay, and then it drops off on either side. If you go out 1 standard deviation, it depends on the type of test. It's either 10 or 15 points, but if you go down to 90 and up to 110, for example, on most IQ tests, you will capture about 66% of everybody. And if you go out another, you go down to 80 and you go up to 120, you'll capture about, I think it's about 93% of people altogether. I should do this down here. And if you go out another 3 to the 3rd standard deviation, you capture about 99.5% of all people. Okay, so that means that almost everybody walking around has an IQ between 130 and 70. It's another thing, if you go online and you take your IQ, you will be a lot smarter than this because they're trying to get you to click on stuff and they also want you to buy stuff. So they're smarter than you. So if you take an IQ test online, you're not really going to get terrific, you're not going to get accurate results. But so this is true for everybody, but do you think this distributes equally among like different professions? Yeah. So there are some really interesting things, like because we're engineers, I'll put that engineers average IQ tends to be about 115. Then, and it has a pretty, I don't know how you put this, pretty small spread. It's about 105 to, it's actually kind of skewed upward, so about 130. Physicists tend to skew higher. Their average is about 120, and there's almost nobody down here, so they skew from about 110 to quite high, 165 plus, which when you get to about 165, you really can't measure anyone's IQ anymore. It's just like, who, I mean, how would you measure it? Who would be doing that? We don't know. We don't know what's going on in there. But there are some people who like have reported IQs that are quite incredible. There's a woman named Marion Vosavant who has the world's highest reported IQ, and it's supposed to be like 220 or something like that. So I don't know. But anyway, other professions. The other thing is like, and I'll just leave you with this idea. So if you work in a business environment and you look at file clerks, they have a huge range of IQs. It goes from about 80 to about 130, maybe even 140. The reason, and this is really strange, I mean, it looks really strange, but when you think about it, what really happens is people tend to enter the business world in a very menial kind of a job. And so what happens with file clerks is everybody comes in here and then they sort into different jobs later on. So there's some reasons for that. The one that I found kind of, I don't know if I would say disturbing, but medical doctors have a good, like about a 130 on the top end, like engineers, or maybe a little bit higher than us. But they go down to like the same, like 105. And I thought, I wonder what a doctor down in this range looks like, you know, because you really want a doctor to be able to diagnose you and be able to find some interesting data and put things together in an interesting way. So I don't know what these guys are doing. I don't know how they got into medical school. I don't know anything about that, but it's just kind of an interesting effect. The last thing, and I'm going to let you go because I said I would, if you look at a lot of human behavior issues, if you look at men and women, the average tends to be just exactly the same. And this could be anything. This could be like work ethic or psychopathology or violence or nurturing. The averages tend to be just exactly the same. But something happens really strangely is that women's data tends to cluster at the mean and that men's tend to flatten out a little bit. So what you see is here in the extreme, you get a lot of extreme behavior that men or males exhibit more strongly than women, and that's on both sides. So more men are capable of, or I shouldn't say capable, more men tend toward violence and more men tend toward heroism, being heroes. More men tend toward not working at all, and more men tend to work 85 hours a week. So when you look at those extremes, sometimes like you look at people in our society, I was thinking about this, like you think about people like who are kind of like larger than life, like Elon Musk or Richard Branson. You really can't make any correlations with them with other human beings, male or female, because they're really operating on their own sets of principles. If you look at like serial killers, people who've perpetuated bank robberies, they always tend to be like that. And then having said that, the last thing I will say is this, I guess that's just where I want to make that point, is that you have to be really careful when you look at those outliers, because you don't really want to make assumptions about a general population based on something that's very visible. And so, so that's just kind of an interesting fact. It's kind of like when you look at math ability, for example, that's another characteristic where men and women have the same average, and women in high school actually do a little better at math than men. But if you look at the extremes of math ability, men pick up those two things as well. So although it flattens out even a little bit more, where there's more people in here who are male, who have very high math ability, but not freakishly high math ability. And so that seems to be a reason why men tend to go into math-based professions more often than women, whereas women tend to have higher amounts of empathy, and that makes them go into people-oriented professions more often. So that's what I wanted to let you know about statistics, except for the fact that, like I said, Excel is going to be your new best friend, and I will be in lab this afternoon. So if you need some help, come on over and we'll work on some statistics in Excel. So